Okay, another important thing about equilibrium is a concept called reaction quotients. And it's really not about equilibrium itself, it's about where a reaction is with respect to equilibrium. So if we're thinking about precipitation and solutions and solubility and how much solid is going to dissolve in a solution, then if we know some information about the concentrations of each of the ions present, then that's going to give us an indication of how close we are to equilibrium. So we have seen reaction quotients before with our Q values. Q can have a number of different subscripts depending on what it actually is representing. So for example, Q sub C has the same expression as Kc, right? The equilibrium constant with respect to concentration, or KEQ is another way that you often will see this. You could have a QEQ also. In this context, we'll just call it Q, and again, it has the same expression as KSP. And in this context, we call it the ion product. Which kind of makes sense because the KSP values don't include the solid. So when we're thinking about the solid dissolving in solution, then the product of the ions present raised to their the exponent of their coefficient is what we're talking about for the KSP value. So this is called the ion product. And again, the same rules apply. So kind of the value of Q compared to KSP gives us information about where we're at with respect to equilibrium. So if Q is less than K, then the reaction hasn't reached equilibrium yet. It's smaller than KSP, so the reaction's going to still move forward. If Q is greater than the equilibrium constant, then that means we've overshot equilibrium. We have to go backwards in order to reach equilibrium. And if Q is equal to KSP, then we're at equilibrium. I like that I put a comma there. If this, then arrow. Okay, so let's think about this for a second. Which one of these scenarios would result in more precipitate forming? And hopefully you're kind of picturing a reaction and the solid is dissolving. So which one would give me more precipitation, right? It looks like the reverse reaction would actually cause more precipitation. So we'd have to push back the other direction. We'd precipitate more out. That would get us back to equilibrium. So that's kind of interesting information if we have some conditions. So let's take this problem that I've set up here. I have lead iodide. It's one of my go-tos. It's just so pretty. I love that it's yellow. If I have a concentration of lead ions of 3.0 times 10 to the negative third molar, so we're talking molar concentrations here, moles per liter, and I have this many of my iodide ions, and this is my KSP for this reaction. Again, KSP's being small like this means that it's a fairly insoluble solid. If we were to look at our solubility tables, we would look at that and it would say that it's an insoluble solid, but kind of the degrees of that come from our KSP values. So our expression for Q, our reaction quotient, or our ion product in this case, is going to be the same as my expression for KSP. So it's going to be my lead times my iodide squared. And the reason we're using Q and not K is we don't know if we're at equilibrium. So I have these concentrations. These are something that I could measure. So I used some sort of ion chromatography and figured out how much I had. And then now I can say, well, am I at equilibrium? Or where am I with respect to equilibrium? So now if I say, I'm just going to plug in these values then. Here's my lead. Here's my iodide. And I end up with 4.8 times 10 to the negative 10th. And 2 sig figs along the way here. So when I compare this number to my KSP, I say, well, this number is smaller, than this one. So because this one is smaller, it means that we haven't quite reached our equilibrium yet. We're still going to have to move this forward reaction before we can actually get to equilibrium. So what this tells us then is that the reaction is going to move forward. And remember that that's just kind of the way that we define it, that the forward reaction is left to right, the reverse reaction is right to left. So the direction is moving in the forward reaction, or it's shifting towards the products, if you wanted to think about it that way. So the question, though, is will we precipitate out lead iodide? So am I going to get more solid? And the way that we can answer that is no, we're not going to get more solid, because we're actually going to get less solid because we're shifting towards the product. So we need to dissolve more of it in order to get to equilibrium. So no is the answer. Now there's some practical medical kind of applications to this as well. If we look at this problem, for example, calcium phosphate is one of the compounds that is responsible for kidney stones. They're actually a combination of a number of different fairly insoluble compounds. And if you have the right concentrations, or rather the wrong concentrations of calcium and phosphate in your kidneys, then that can cause, that imbalance causes stones to form, one again of many things. So if we kind of oversimplify and say that that's the primary responsibility of the calcium phosphate, we have this much of each of them. So are we going to get kidney stones? This is a very small KSP. So if we're comparing this to our lead iodide, we just saw that it was on the order of 10 to the negative 9th. This one is on the order of 10 to the negative 26th. So now as we're starting to see values of KSPs, we can see that definitely some of these solids are more insoluble or even less soluble than others. And there's just kind of a spectrum for that. So usually in general, we blanket say, these things are soluble, these things are insoluble, these things are slightly soluble, but there's degrees kind of all the way across the map here. Okay, anyway, so if we were thinking about the Q value here, our ion product or our reaction quotient, then the expression for that is going to be the calcium ions cubed times the phosphate ions squared in accordance with my reaction here. And I'm given concentrations for each of those, so I'm going to plug those values in. And when I run the numbers on this, I end up with a Q value of 3.9 times 10 to the negative 19th. And so I'd say, okay, well, let's compare this to KSP. So this number is larger than my KSP. So if I have a larger Q than a K value, that means my reaction is going to shift towards the reactants. So we're going to, the reverse reaction is moving forward, if you wanted to think about it that way. Let's just say that the reaction is favoring the reactants. And again, the goal of this is really to reach equilibrium, to attain equilibrium. So we need to shift towards the reactants. So what does that mean functionally for this particular reaction? I had ions in solution. If it's shifting towards the reactants, that means more solid is precipitating out. So yes, we are getting more kidney stones. Which one doesn't usually say yes to kidney stones, but that's what's happening in this particular reaction. So this is kind of one of the ways that if we're given concentration information and we know our KSPs, then we can run the numbers using this reaction quotient or the ion product in order to figure out, well, where are we? What can we predict about this system? What's going to happen? Are we going to get more precipitate? Are we going to get less precipitate? And then what are the conditions? What are the things about the conditions I can tweak in order to make more or less of this happen given these concentrations? So that's kind of how you can use some of this kind of stuff.